Hello, and welcome to the Deep Dive. Today, we're going to challenge a really big assumption that's, been dominating tech for a while now.
Right.
The idea that when it comes to artificial intelligence, bigger models are always better models.
That's it, exactly. The sources we're looking at today paint a really compelling picture that the future of AI isn't necessarily about building the next giant frontier model.
Okay.
Our mission here is to really dig into the evidence that shows that smaller, specialized, and just fundamentally different models are what we need to solve some major roadblocks.
Roadblocks in what area specifically?
In reliability, in efficiency, and even in core reasoning itself.
So we're going to look at three key counter-arguments to this whole scaling paradigm. First up is reliability through specialization.
Yep, then efficiency through localization.
And finally, a really fascinating one. The future of actual reasoning through architectural depth, not width.
And at the heart of this whole conflict is, the technology we all know.
Yeah.
Yet large language models, or LLMs.
Mm-hmm.
They're built on this idea of vast, centralized processing. And, this is the key part, probabilistic reasoning.
Meaning they're designed to guess, to predict the next word based on all the data they've seen.
Precisely. And while that approach is, it's fantastic for things like creative writing or summarizing an article,
Sure.
it creates these serious gaps when you absolutely need to trust the answer. It limits where you can use them.
Especially in high-stakes fields.
Absolutely. Think about medicine or finance or the law.
Oh.
You need answers that are verifiable, that are auditable. And probabilistic outputs just aren't good enough.
Why not? What's the core failure there?
It's that they often lack provenance. They can't definitively tell you where they got a piece of information from.
Ah, so you can't trace it back to the source.
You can't.
Hmm.
And they also lack the kind of structural rigor you need for formal systems.
Okay, so let's unpack this reliability problem. Let's start with why these massive general LLMs seem to fail when we ask them to create, structured, reliable knowledge.
Yeah, so the problem really comes up when these general LLMs try to build something called a knowledge graph, or KG.
From unstructured text, like a bunch of research papers.
Exactly. Because they're trained on this, world-scale data, the whole internet, basically, their expertise in any one domain is actually pretty shallow.
So they make mistakes.
They do. They're prone to factual errors, they hallucinate relationships that don't exist, and their answers can change dramatically if you just slightly change the prompt you give them.
Okay, hold on. Let's quickly define knowledge graphs for everyone listening, because that structure seems really central to the solution here.
It is. A knowledge graph is essentially knowledge in its symbolic structural form. It maps out relationships very clearly.
So instead of a sentence.
Right. Instead of saying metformin helps people manage blood sugar, a KG represents that as a clean, structured triple. Metformin treats type 2 diabetes.
Which is valuable because it gives you things an LLM can't.
Two critical things: interpretability and auditability. You can trace every single piece of information.
So the goal is to get that structured rigor, but you still need the flexibility of an LLM to read all that messy, unstructured text in the first place.
That's the challenge. And that brings us to this idea of neurosymbolic AI.
The best of both worlds.
Pretty much. For decades, you had symbolic AI, which was rigorous, but, couldn't handle noisy real-world data. Then you had neural AI, which is great with noise, but it's a black box.
You don't know how to answer.
You don't. Neurosymbolic AI is the synthesis. It uses the neural part for pattern recognition and the symbolic part for rigor, for rules, and for transparency.
And the sources point to a specific model, a specialized one called GraphMERT, as a sort of champion for this approach.
Yes.
And this model is small, but it punches way above its weight, right?
It's a remarkable counterpoint to the whole bigger is better obsession. GraphMERT is tiny. It's an encoder-only model with just 80 million parameters.
80 million! That's hundreds of times smaller than the big frontier models.
It is. And its entire purpose is specialized: to distill reliable KGs from documents, focusing on two things above all else: factuality.
Meaning, can you trace it to a source? Provenance.
Exactly. And validity, which means it follows the rules of the domain and is internally consistent.
Okay, and we have the data to back this up. How does this tiny specialized model actually perform against a massive general-purpose LLM on a really high-stakes task?
Yeah, the comparison is pretty stark. We have data comparing GraphMERT against a powerful baseline, Qwen 332b, which has 32 billion parameters.
Okay.
They were both given the same task.
Yeah.
Extract knowledge graphs from real PubMed papers about diabetes research.
Yeah.
And the difference in reliability is, well, it's something every one of these fields needs to see.
So give us the numbers.
GraphMERT achieved a 69.8% fact score. Now, fact score is a metric that measures how precise the extracted fact is when you check it against the original text.
So it confirms it wasn't just hallucinated.
Exactly. Baseline LLM, Quen 332B, scored only 40.2%.
Wow. That is a staggering difference. A model that's hundreds of times smaller is almost 30 percentage points more factually accurate.
Right.
If you're building a medical knowledge base, that gap is the difference between something that works and something that's a huge liability.
And it's not just that.
Yeah.
The validity score is just as important. That checks if the facts align with the domain structure. Did the model get a relationship backward or misclassify something?
And the results there.
GraphMERT scored 68.8% on validity, the massive LLM, only 43.0%. This specialization just allows for an audit trail and prevents these basic logical errors that general LLMs make all the time with structured data.
So specializing for reliability is clearly the winner in these high-stakes areas. But reliability, that's not the only problem with this bigger is better mindset, is it?
It's not at all.
The massive scale of these general models is creating an unsustainable infrastructure burden.
Exactly. The energy, the sheer compute requirements,
Yeah.
they're staggering. We're seeing projections that global data center capacity could nearly triple by 2030.
And that's mostly driven by AI.
Overwhelmingly by AI inference workloads. The centralized cloud-only model is just fundamentally expensive and, frankly, environmentally stressful. Which brings us to the efficiency argument.
Which is all about moving that computation away from the big data centers and back to our own devices, to the edge.
That's the idea.
What's making that a real possibility all of a sudden?
The short answer is just the dramatic improvement in small language models. We're
Right.
talking about models under about 20 billion active parameters.
Okay.
They become so efficient and so capable that the local accelerators you have in, say, a modern laptop or a smartphone can actually host and run them with very low latency.
And to measure how viable this local approach really is, we need a new way of thinking. The sources introduce a metric called intelligence per watt, or IPW.
IPW is the new governing metric. I think of it like miles per gallon for AI.
Oh, I like that.
It measures the task accuracy you get divided by a unit of power. It really captures that essential trade-off. How much intelligence can we squeeze out of a limited power budget?
And what's the data telling us about how IPW is progressing? Is this local efficiency boom something that's coming, or is it already happening?
It is happening, and it's happening fast. In just 2 years, from 2023 to 2025, the industry saw a 5.3 times improvement in IPW.
5.3 times.
Yeah. And it wasn't just one thing, it was compounded progress. About 3.1x came from smarter, smaller model architectures, and another 1.7x came from better hardware.
A 5-fold efficiency gain in 2 years is just, it's astounding. What does that actually mean for us? Like, how much of our normal AI workload could we really move to our local devices?
Well, that boom means the number of queries that can be handled by a local LM tasks that don't need a massive cloud model, it just skyrocketed. It went from about 23% in 2023 to a projected 71% in 2025.
71%.
And the data also shows that these local LMs can successfully handle the vast majority. We're talking 88.7% of common single-turn chat and reasoning questions.
That completely changes the economics. If almost 90% of my quick questions can be handled right here on my device, I don't need to send every single query to some expensive, power-hungry cloud server.
Precisely. And the biggest benefit comes from a hybrid strategy. You use an intelligent query router.
Oh, little traffic cop, basically.
A traffic cop, yeah. It decides, can this be handled locally, or does it need to go to the big frontier model in the cloud? The savings are transformative.
Okay, so let's imagine a perfect router, like a theoretical best-case scenario. What kind of savings are we talking about?
The reduction in waste is enormous. An Oracle router like that could cut overall energy use by 80.4%, compute cycles by 77.3%, and the actual cost by 73.8%.
Compared to just sending everything to the cloud.
Compared to a cloud-only deployment, yes.
But what about in the real world? Even if our router isn't perfect, if it makes mistakes sometimes, are the savings still significant?
Well, they're substantial. Even a practical router that's only 80% accurate in its decisions still gives you huge gains, like a 64% energy reduction and nearly a 60% cut in compute and cost.
So the move toward local, efficient models seems inevitable just from a practical standpoint.
It's the future of widespread AI deployment, no question.
Okay, so that covers reliability and cost. Now let's pivot to the most fundamental challenge of all, core reasoning. Why is it that even the biggest, most scaled-up LLMs still struggle so profoundly with complex multi-step logic?
This is the third argument, and maybe the most important one. The standard transformer architecture, it doesn't matter how many billions of parameters you give it, has a fixed computational depth.
What does that mean, fixed computational depth?
Think of it like an assembly line. You can make that line incredibly wide, you can have tons of workers, those are the parameters, but the process always involves a fixed number of steps, one after the other. It never changes.
So when people use the technical term lower computational complexity classes, that's what they're talking about.
That's it. Fundamentally, it means that assembly line can't loop back on itself. It can't try a few steps, realize it's the wrong path, and then go back and try something else.
Which is exactly what you need for complex reasoning.
Yeah. Exactly. Something like solving a hard Sudoku puzzle requires search. It requires backtracking. And since the standard transformer is stuck with that shallow, fixed depth, it just it can't execute the kind of deep algorithmic thinking needed for those problems. Making the model wider doesn't fix the depth issue.
So the solution isn't a wider assembly line. It's an assembly line that can dynamically add more steps or repeat cycles depending on how hard the problem is.
You've got it. And that brings us to the Hierarchical Reasoning Model, or HRM. This is a tiny model, only 27 million parameters.
Tiny.
But it succeeds by dramatically increasing its effective computational depth using a recurrent architecture that's actually inspired by the brain.
How does that brain-inspired design work? What does it do differently?
Well, it separates a complex task into two interdependent parts, sort of like how our brains separate long-term planning from short-term calculation. You have a high-level module, the H module, which is the slow, abstract planner. It keeps track of the overall strategy.
That's the manager.
It's the manager, exactly. And then you have low-level module, the L module, which is the high-speed worker. It does all the rapid detail computations, the intensive search.
And what's the key interaction between them?
The key is that the H module, the manager, can systematically reset the L module. This lets the whole system run these very deep, nested computation cycles. It can do systematic search and backtracking in a way a standard transformer just physically cannot.
And the results from this different architecture are, from what I've seen, just astonishing, especially when you put it up against the big chain of thought LLMs that are supposed to be good at reasoning.
The performance gap is definitive proof that size is just irrelevant for these kinds of tasks. HRM got near-perfect scores on the hardest Sudoku puzzles, which require a huge amount of search. It also found the optimal path in large 30 by 30 mazes.
And how did the big LLMs do?
In both of those cases, the massive state-of-the-art chain of thought models, they failed completely. 0% accuracy.
0%. That's not just a small difference in performance. That's a total architectural failure to even address the task.
It is. And what's more, on the ARC-AGI-2 benchmark, which is a standard test for general fluid reasoning, HRM, which was trained from scratch on only about 1,000 examples, substantially outperformed the general models. HRM got 40.3% accuracy versus just 21.2% for a much larger commercial model like Claude.
So it can discover complex algorithms from just a tiny amount of high-quality data.
Yes. It just bypasses the massive data requirements and the built-in computational limits of the current LLM reasoning methods. We're seeing a shift from general-purpose models struggling with logic to these smaller, architecturally superior models achieving mastery.
It's a complete reversal of the current narrative.
It really is.
So what does this all mean for you, for anyone listening and looking toward the future of AI? We've really laid out 3 clear pillars of advancement here that all reject that scaling dogma. We have reliability from neurosymbolic models like GraphMERT. We have efficiency from local computing and the IPW metric. And we have true reasoning depth from brain-inspired architectures like HRM.
The essential conclusion from all this research is that the next big leap forward won't come from just scaling up. It hinges on smart integration.
What kind of integration?
We need these reliable, factual knowledge graphs and other explicit high-level structures to guide the efficient approximate inference that neural networks are so good at. That integration, that's the necessary step toward what you might call domain-specific superintelligence.
And this just flips the whole narrative on its head. The trade-off between quality and quantity becomes the central issue.
Absolutely.
If a specialized model like HRM trained on just 1,000 well-chosen examples can fundamentally outperform a vast model on complex logic, it tells you that high-quality data and the right architecture are far more important than just sheer volume.
That's the bottom line.
So we have to ask, what domain in your professional life or even your personal life could be totally revolutionized if the focus shifted away from massive breadth and toward cultivating specialized depth? That's the question we'll leave you with until the next deep dive.